As part of the Mechanical Engineering Systems course, ME435 at Pennsylvania State University, our team has been tasked with programming a JetBot to navigate autonomously. The JetBot is placed in a setting similar to a road in a small town and needs to be able to follow some basic driving cues. Throughout the course of 3 laboratory sessions, our team assessed motor bias and kinematics and added line following, image recognition, path planning, and robot-to-robot communication capabilities to our JetBot. In the first laboratory session, our team started by testing the behavior of the differential motor system in the JetBot. We found that inputting equal positive values to each motor resulted in the robot moving in a forward motion in a straight line. Providing a larger value to the left motor would cause the robot to turn right and vice versa. Providing equal magnitude values of opposite sign causes the robot to spin in place. Finally, 2 negative motor values resulted in a backwards motion, with the same logic applying to turning rules for forward motion. Next, we tested for motor bias. Our team measured a distance of 4 feet and provided equal positive motor values to each motor. After the robot traveled 4 feet, we measured how far to the left or to the right that the robot deviated from its starting point. For this experiment, any error greater than 4 inches was considered user error and attributed to incorrect placement of the robot. Additionally, we recorded the elapsed time for each trial, which allowed us to calculate the velocity of the robot. We found that at lower speeds, our robot experienced a small bias and required correction to drive in a straight line. At higher speeds, there was no difference in individual motor speeds. In the second laboratory session, our team first added the ability to follow the dotted yellow line in the center of the road. The first step in following a line is to be able to detect the line through image processing. To process the image, we first convert the camera image from RGB to HSV color. Because the center lane of a road is yellow, we use known HSV values for yellow to create a color segmentation mask based on HSV thresholds. Having developed an image filter, our team calculated heading angles to inform the robot's steering. To determine the heading angle, we used inputs from the camera to determine how far offset the center of the image is from where the robot is looking to the line on the road. Finally, our team developed a PD controller based off of this angle calculation. Given that the desired angle to follow the road is 0 degrees between where the robot looks and the center of the road, the angle reading is used as the input error. This means that based off of whatever angle the robot detects, it will adjust its steering based off of both the derivative of its angle and the current angle proportional to whatever reading it receives. Also in the second laboratory session, the team trained a model that allows the robot to determine whether a stop sign, speed limit sign, or no sign is present. To create our model, we took 30 pictures from each category, 90 total pictures. After taking these pictures, we trained and tested our model and found that it could easily identify stop signs and speed limit signs, but struggled to tell if there was no sign or a stop sign. To increase the robustness of our model, we used a total of 120 images that had no sign. After adding these images, the robot can reliably predict whether or not there is a sign. To understand the importance of this ability, we sat and talked with one mechanical engineering student at Pennsylvania State University. Why is this pattern recognition technology important?
Well, Elliot, about 140,000 people every year are hit by cars according to the National Highway Traffic Safety Administration. So we are willing to accept this when it comes from people, but if a single autonomous car hits a pedestrian, then that makes national news. So it's a little bit unfair in the public consciousness. So it's very, very important that we get this right as close to 100% of the time as we can. The ability for self-driving cars to recognize other vehicles, pedestrians, and traffic signals is essential for the development of future cars.
The third laboratory session focused on path planning. In order to plan a path, our robot needs to know its current location on the map and its destination. To access the live location of the robot, we used an April tag system. April tags are similar to QR codes, but are designed to encode far less information, only 4 to 12 bits. According to Dr. Edwin Olson, of the University of Michigan, the small amount of information contained in an April tag allows it to be detected robustly and from long ranges when compared to a QR code. Our robot has one such April tag mounted on top, which can be detected by an overhead camera that is mounted from the ceiling above our map. By assigning a global coordinate axis, we can determine both the robot's global position relative to an arbitrary origin point, as well as its orientation relative to our axis. Assessing live pose and location data enables the robot to create new paths and follow them at any moment. To plan a path, we first need to capture and scale an image from the overhead camera. By measuring the length of items on the map and comparing it to the number of pixels in the image, we can convert all lengths in pixels to centimeters. Next, we converted our map into a binary map by setting the color threshold that determined if a pixel would be black or white. We adjusted this threshold until only the roads were white and all of the off-road places are black. This binary map indicates which locations are valid points for the robot to plan to drive with white pixels. Were there any complications when using the overhead camera for an image to make a map?
Yeah, so the image from the camera has barrel distortion, causing the center of the image to look larger than the edges. To fix this, we needed to make a camera correction matrix which adjusted the pixels to create a flattened image or undistorted image that was suitable for mapping.
With our binary map, we can input the current location and a target location to our code, and the code will produce nodes spaced across the road. Next, we can adjust the number of nodes, the distance between them, and the maximum number of node connections to find the shortest possible path to our target destination. Finally, our team developed an algorithm that allows the robot to make decisions at an intersection based off of the intended path. Because the robot uses line following, and there are no lines in the intersection, we need to implement a decision process to successfully navigate intersections.
So this flowchart represents the code that would be needed to have a JetBot go from point A to B while following the road and traffic signals and optimizing its path for the shortest route. So to start, it needs to first know its initial location where it has to communicate with the camera bot, and then that will use that as an input and the final destination as an input for path planning. And then using the different nodes, it should decide whether to turn or go straight using the kinematics with the left and right wheel. And then while all that is happening, they will also alternate between following the road and following the road signs, because the camera can only do one thing at a time. So it will check for signs intermittently and obey all the traffic signs and be able to recognize them. And then with all of those information as input, it will use the motor control as the output, the left and right motors. And then finally, when it's at a node, it should determine whether or not it's the final node, and if it is, then it succeeded and will stop, and if it's not, then go back and start the node again.
For the final project, our team can decide on the extent and the nature of the autonomy that the JetBot has. There are 5 total function choices from the laboratory experiments: kinematics, line following, pattern recognition, April tag recognition with robot-to-robot communication, and pathfinding. Our team must complete at least 2 of these objectives. We chose to program the JetBot to follow lines, determine position, and make turns using kinematics. In our program, the first thing that the JetBot does is communicate with the camera bot to retrieve its location using the April tag. Next, it makes a left turn that has been programmed based off of the desired turn radius from measurements of the course. After completing the turn, the line following algorithm described from Laboratory 2 begins, and the JetBot will continue to follow the line. In summary, our team added several functions to the JetBot that allow it to navigate autonomously. In the first lab, we tested kinematics and motor bias. Next, we explored image recognition and line following in the second lab. Finally, we created an algorithm for path planning in the third lab. To incorporate these capabilities into a single code, we created a comprehensive flowchart. This flowchart guided our team through the final project, where we developed a code that demonstrates understanding of kinematics, line following, and robot-to-robot communication with April pegs.